All right, Chapter 11, Section 6, Surface Areas and Volumes of Cones. This progression through three-dimensional objects, since Section 4 really, has followed this similar pattern. There's a reason why they give the order that they do. Recalling us back to Section 4, when we first introduced the concept of these three-dimensional solids, and namely the umbrella category of what we call polyhedra, where I have some three-dimensional shape which is surrounded on every side by polygonal faces and stuff like that. Okay, however complex that may be. Back in Section 4, when we introduced that term, we broke it down to two families of polyhedra that we called prisms and pyramids. Okay, and then there were the non-polyhedra, anything with a curved surface, like cylinders or cones that we're dealing with here in this section, anything else that had curved surfaces like a sphere. Those were non-polyhedrons. That being said, there's a lot of similarities in measurement between those two families, the polyhedra and the non-polyhedra. And it really breaks down to similar shapes. In Section 4, just to recall us back to that, we talked about two types of three-dimensional objects, prisms, or as many of my students think of them as crystals or tubes, okay, where there were two congruent polygon bases separated by a series of rectangular sides, okay? And then it was in the same category as cylinders, which were basically, or like Pringles cans, tennis ball cans, whatever you think of them as. But cylinders are basically the circular version of a prism. And they both had the same volume formula, where it was capital B times H, the height or altitude or depth of that figure. And capital B was the area of the base. The difference was that with the cylinder, the area of the base was a circle. Okay, that was dictated for definition of a shape of a cylinder, as opposed to the polygonal shape of a prism. The reason I'm bringing that up is because in Section 5, we introduced pyramids, the second namesake, the second family of polyhedra in that category. And pyramids had a single polygon base, and then a series of triangles on each side that met at some apex, the top of that pyramid. And the formula for volume of that pyramid was 1/3 of the area of the base times the altitude, the height, the depth of that pyramid. And the reason we're moving now into cones is because the cone, much like the cylinder, is the circular version of its counterpart. A cone is just a circular version of a pyramid. It even visually looks like a pyramid. It's just now a circle base. So we're going to see that reflected in the second clip when we're talking about the volume of a cone. It's the same exact formula as the volume of a pyramid. It's just that now when I'm finding the area of the base, that base just happens to be a circle. But in this clip, I wanted to talk about the first namesake here, surface area. The surface area of a cone or any three-dimensional shape is one of the most abstract concepts in the entire geometry subject. And it's the most abstract for a simple reason. It requires us to visualize or even just look at a three-dimensional object, whatever that object is, and unravel it. Because surface area, if we think about it in terms of the cone that we see here on the screen, in order to unravel this to think about the material that would make each surface, I might separate out the circular base and then like maybe take an imaginary pair of scissors and cut along the side of the cone's side and then unravel that. And I'm going to end up with an object that looks a little bit like this. Something that's very tough to just visualize. This kind of circular shape and what looks like a Pac-Man type of mouth on the side of it. Okay, and the equivalent here of unraveling things, and just wait until we get into spheres in Section 7, how that unravels. But anytime we're like abstractly, mentally unraveling these objects, it's kind of the equivalent of like getting a package from Amazon in the mail and you're kind of unraveling the box, breaking it apart to put in your recycling bin. Okay, when you spread it out, like it's almost unrecognizable from the three-dimensional object it made. So this is definitely an abstract, tough subject to wrap your mind around. So whether or not you're an expert drawer or something like that, artist, kind of converting these things, these three-dimensional objects, into their two-dimensional unraveled surface area, understanding the formula is going to be a little bit more important. Okay? And so the important thing to understand here for surface area of a cone, or a pyramid for that matter, is that it basically breaks up into two separate pieces. Whatever shape base there is, and for a cone, that base is a circle. And so for the area of that base, it's just going to be pi r squared. So in my surface area formula, this first piece right here is the area of that base. Had I been unraveling a pyramid, it would be the area of whatever polygon was that base. Okay, so this first piece of the formula for surface area is just that area of the base. This happens to be a circle, pi r squared. When I unravel the side of a cone, this one tends to be a little bit more difficult to grasp, but we end up with this kind of shape. And so if you can imagine it, this Pac-Man mouth, if I were to, say, take this bottom piece of the mouth right here and try and touch it to this top piece of the mouth right here, it's fundamentally going to curve it upwards, right? And that's what's going to make that cone shape. So when I unravel it to get this Pac-Man mouth, and some of you guys have done this before in other like grade school like craft projects and stuff like that, that's where the cone shape comes from. And when I unravel it, I end up with this Pac-Man mouth shape. So this ends up being the tricky guy to find the area of, and I'm going to kind of skip over some of the proof of it, but it breaks down to this formula right here. Pi times r, and then we insert this cursive L. Right? Pi and r are going to be familiar ones at this point. Pi 3.14, just pi. R being the same radius as the base of the circle. But this cursive r is the new term right here, and that's where we're going to introduce what's called slant height. Slant height. That's going to be the distance from the base along the side of the cone up to the apex or vertex of that cone, the top of the pyramid, if, to use the pyramid term. So slant height is the actual length along this side. That is fundamentally different than what we've been doing for volume. With volume, I care really only about the height or altitude or depth of my three-dimensional figure. And that still will be an important measurement when it comes to volume in the second clip. So the height, the altitude, the depth of a cone still is important for certain measurements. But when it comes to surface area, the piece I'm actually going to care about is the slant height. And I'll talk about variations we'll see where, depending on the information we're given in a diagram, how we can find these other pieces. But suffice to say for now that within this surface area formula, the piece that I'm going to need right here, this slant height, I'm going to need that for this second piece, this unraveled side of the cone, what will make a Pac-Man mouth. I need that for that second piece. So the two pieces, again, that are created here when I unravel this cone are the circular base and what we call the lateral surface area, or the side of the cone. And it's worth pointing out here that even though this formula may look a little intimidating, as long as you have it written down, you don't have to memorize it. But also, there are really only three objects to know the measurement of here. Okay? Whether I'm solving for it or I'm given the information explicitly, capital S is the surface area, the actual two-dimensional area of the material that makes up the cone. Pi is an actual real number. Okay, so that's not a variable. R is the radius, the distance from the center of the base to its side. Okay, radius. That's the same exact R as this R. Those are the one and the same. So as long as I know the radius, I actually have two things to input it into in this formula. And then the third and final measurement I need to know is this cursive L, the slant length, the slant height. Again, the distance along the side of the cone, the length of the cone, so to speak. Okay, so let's apply this to an example. And again, I'll talk about variations we might see. So at the bottom of your screen, you'll notice that we are given an example. This is pretty typical of the problems you're going to see at the beginning of your Section 6 assignment. You'll be shown a cone. You'll be given some measurable information about that cone. And thankfully, in this example, the pieces of information we're given are things that we can directly plug into this formula. Again, I'll talk about variations you might see and how you can solve for the pieces that you need. But let's go ahead and jump to the whiteboard so that we can work through this problem. It'll be a very fast solution for this specific one, but the variations will be the pieces that we're going to talk about mostly here. Okay, so we're given a cone. We're told that the distance from the middle of this cone to the side, the radius, the lowercase r in our formula here, is 4 inches. We are told that the slant height, which will typically be shown like this in your diagrams, where they're actually showing the distance along the side of the cone, this one was told to be 6 inches. I'll talk about different ways they might show you information where you can still find that slant height. But for the sake of this problem, that 6 inches will be the cursive L in my formula. So now I just jump to the formula. Surface area is equal to the sum of the two area pieces that I can break down here. There is the base, which I'll color in blue right here, which again is a circle. So that's just going to be pi r squared, the r again being that 4 inches. And then the other piece that I can unravel here is what makes this actual cone itself, what we call the lateral side, the actual side of the cone. So if I think of this as like an ice cream cone, this is the waffle cone itself. And for that, it's pi times that same r, that 4 inches as the r for the pi r squared, times the new term, the cursive L, the slant height, which in this case, the cursive L will be the 6 inches. So at this point, I'm just plugging in the information I know, solving for the surface area that I don't know. So when I plug this in, r is the 4-inch radius at the bottom there. So this is just 4 squared. And then for the lateral side, I'm going to have pi times that same 4 inches, the distance right there, times the slant length here, which is 6 inches. There's the simple substitution. This is still all equal to the surface area of the entire cone. So I'll work through the exact solution, keeping pi as pi, and then I'll show you at the very end how you just plug in 3.14. But let's first deal with this piece. 4 squared, or 4 times 4, gives me 16. So the actual area of just the base is 16 pi in exact terms. For the lateral side, 4 times 6 is 24. And then just keeping the pi in there. So the area of the lateral side, the actual side of the cone, is 24 pi. And so surface area is the sum of these two pieces. And even though it's not a variable, pi does make a like term here. I can actually add these two things together. In exact terms, 16 plus 24 is 40. Surface area of this cone is 40 pi. The units here are in inches. And this is area, so they're square inches. The units will typically be given to you in big ideas. You'd have to solve for this piece. This would be the exact solution, 40 pi. Again, worthy of working it to this point either way, because in big ideas, again, they'd like to mark you wrong, even if you're off by like 0.05 or something like that. So wait until this point to plug in 3.14 for pi. So now if I had to round to the nearest 2 decimal places, I would do 40 times 3.14, about 125.6 square inches. And then to 2 decimal places, I would just add in the 0 right there. So this right here would be my answer for the square units, the area of the material that makes this cone. Again, if I were to think of it like an ice cream cone, this is the batter that makes the container, also including the base. So really quickly, I just wanted to show you a variation of this problem, where maybe instead of giving me the slant length, like they did explicitly here, the 6 inches, another thing they could have done is this. And so you could just write this in your margin. You don't need to like treat this as its own problem. Another thing they could have done here, just to finish out this clip, they could have still told me that this down here was 4 inches, the radius of my base. But then they could have told me the altitude, the depth, the height of my cone, right? So they could have told me this value, which in my volume formula is h. And just to point this out, this is now a right angle. This is a height. And here's what I wanted to point out. This is now a right triangle, meaning I can apply Pythagorean theorem to it. So if I needed to find my slant length cursive L right here, I can use Pythagorean theorem to establish this 4 squared plus whatever this altitude is squared. It has to be equal to this slant length squared. So that's just a different way it may be expressed, and that's how you would solve for cursive L.